Assalamu alaikum everyone. In today's lesson, we would be um, discussing about what the ultraviolet catastrophe was, what Max Planck did, and how did the the basics of quantum physics were laid. So before we get into what happened later on, we need to understand what the situation at hand was, you know, before all of that actually happened. So at that time, everyone was a believer of classical mechanics. So whatever Newton had given us and other scientists, we believed them to be the absolute laws of physics. All right, and by the end of the 19th century, we had some, we considered that mass and energy are distinct. So that's what we thought till the end of the 19th century, that mass and energy are distinct, and there is no, you could say, intermingling or interchange between the two. So there was no change, interchanging, or intermingling between the two. They were two separate and distinct things, but very drastically, things actually changed. So let's first make a comparison of what we actually thought about mass and what we actually thought about energy. So we thought that mass, it consisted of particles, and energy, let's say in the form of light, consisted of waves. We also thought that mass, it as the name suggests, it has mass, whereas we considered that energy was massless. We also considered that the position of a mass, it could be determined, or the position of a mass in space could be defined. So, I could actually tell you where this, let's say this pen in my hand would be placed. I could tell you where a plate would be placed if it's on my table or anything like that. So, in other words, anything that has a mass, I could actually tell where in space is it placed. And whereas for energy, we considered that it was basically, my bad, it was basically delocalized, which meant that we can't really define the position of energy in space. So this is where we were at the end of the 19th century. And along with that, one important thing to note over here is that we considered that energy was continuous. So let's say if I have a band of energy, I would actually, I would see energy all over. There are no gaps. If I have this, if I have this absorption spectrum, actually emission spectrum, I would actually see something like this. So, in other words, energy was continuous. Okay, we didn't really think that energy could have these discrete values, which we will get to that point, but that's where quantum physics comes in. But for now, at the end of the 19th century, we thought energy is continuous. So, for example, if I have this cube, right, and I direct light onto it, all right, there was no limit to the amount of energy that it could actually absorb. It could absorb any quantity of energy, all right. As long as I keep providing it with energy, it will keep on absorbing. So this is what the concept of energy being continuous meant. But then we looked at what we called as the black bodies, all right. And what does a black body actually mean? Black body is basically a body that would emit all wavelengths of the electromagnetic radiation. All right, so maybe you could write that down. A body that would emit all wavelengths of the electromagnetic radiation. What do I mean by that? Now, for a normal body, let's say if I have a normal body and I direct some light onto it, all right, what would happen is that some light would be transmitted, all right, so some light will be transmitted through that material, some of it would be reflected from the surface, all right, and some of it will be absorbed, so some of it will be absorbed, and after some time it will, like, slowly it will radiate that energy out, whatever it has absorbed it will radiate it out, within, let's say, short intervals of time. But a black body, in the case of a black body, what happened was that if we would direct light onto it, we wouldn't see any transmitted light, any reflected light. Rather, all energy or all light, electromagnetic radiation, would be absorbed. So all is absorbed, and therefore what that means is, if all of it absorbed, then basically it would, when it would radiate out energy, it will radiate all wavelengths of the electromagnetic spectrum, right? Because उसने अगर सारी ही वेवलेंथ्स को एब्जॉर्ब कर लेगा इलेक्ट्रोमैग्नेटिक रेडिएशन की, तो वो सारी ही इमिट भी कर सकता. So this is what we consider to be a black body. A very common example would be the sun. The sun is a black body. A hot piece of metal is a black body. Okay, so for a black body, when we used to plot a graph of wavelength on the x-axis and intensity on the y-axis, what the scientists observed, basically with experimentation, they observed that you get a graph something of this sort. Actually, it starts from here, right? And let's say if this is for 1300 Kelvin, if we used to increase the temperature, let's say to 1800, we would see a graph maybe like this. Okay, so this is for 1800, and maybe if we increase it to 2000, we would see something like this. So this is for 2000 Kelvin. Now over here we have the wavelengths, and therefore we have a bit of we could actually divide this region, stating that over here in this range of wavelengths you will get the UV radiation, because you remember the wavelength of the UV light is smaller than the wavelength of the visible light, and which is smaller than maybe of the infrared. So we saw that we had this particular wavelength at which we were getting a maximum intensity at each temperature, and what the scientists at that time stated was that this distribution is only affected by temperature. What that means is that it wasn't affected by the type of material. It doesn't matter what material was that black body made out of. The only thing this distribution was being affected by was the temperature. And what was observed was, as that we were increasing the temperature, okay, as we were increasing the temperature, the wavelength at which we would get the maximum intensity was shifting towards the left. So it was getting smaller and smaller and smaller. Now at that time, this was something which was based on experimental evidence. But in physics, you need to prove something with mathematical operations as well. So at that time, using classical mechanics, the scientists were being unable, they were not able to, basically you could say, using mathematical operations, they weren't able to explain this. They could explain this portion, so they could explain the infrared portion of this graph with the mathematical operations, but they were not being able to explain why this graph was actually dipping at this end. They could not explain the UV radiation side of the, or the portion of the graph. What they actually expected was that this graph, mathematically, with whatever operations they had made at that time, was that this graph should actually keep on increasing and it should actually move to infinity. Maybe I'll use a different color for that. So they, according to their mathematical operations, this graph was supposed to go like this, which technically was stating that as your wavelength becomes smaller and smaller, or when it approximately gets equal to 0, your intensity will approximately get equal to infinity. So in other words, as you decrease the wavelength, your intensity moves towards infinity. And that's not what happens when we look at real life examples, right? It's not as if I decrease the wavelength of the electromagnetic radiation that I'm shining on an object, then the intensity with which it will emit that radiation will just keep on increasing indefinitely. That does not happen. So this was a very big question mark, because in physics we were not being able to define why this is happening. And at this point of time, classical mechanics was actually failing to proving this phenomena. It was a big question mark. And this, my friends, is what we call as the ultraviolet catastrophe. And you can actually see now why it's called the ultraviolet catastrophe, because it was actually in the ultraviolet radiation section of the portion of the graph that we were not being able to define this phenomena. And then at the rescue, we get the scientist Max Planck. You could say he was actually the one of the pioneers of what we define now as quantum mechanics. Okay, so he was actually one of the pioneers for quantum mechanics. So Max Planck actually explained this entire phenomena. He solved the ultraviolet catastrophe. He explained, he looked at these radiation profiles. He came up with mathematical concepts and he presented them, which went hand in hand with the experimental evidence. So what basically Max Planck suggested was that energy, first of all, energy is not continuous. So energy is not continuous as most of the scientists at that time had anticipated. Instead, energy was quantized. Now, before I go into the details, we need to know what quantized means. Quantized means having discrete values. Okay? So, for example, I say that the age of someone can only be 1, 2, 3, 4, 5, 6, 7, and so on, and only up to maybe 100, but not, it can't be 1.2. I mean, someone can be 1.2 years old, because 2 would then basically be, it would come from the number of months, but just, trying to give you the concept that what quantization basically means is that something can only have discrete values. Let me give a better example. Let's forget about the age. You have a switch, right? Electrical switch. It can only be turned on or it can only be turned off. So there are only two possible values, or there are only two possible operations to your switch. You can either turn it on or you could turn it off. So there are only two discrete values in this case. So we could say that actually the operation, or the way that the switch works, is actually quantized. It is either on or it is off. So enough of that. Let's get back to the point that he basically came up with this explanation that energy was quantized. Okay, and he actually gave a mathematical expression to it. What he stated that, and this is quite important, he stated that energy, okay, could be gained or lost only in whole number multiples of the quantity h f, or you could write this down as h v. Okay, and what that means is that this right here, this was h was a constant which was given the name of given the name Planck constant, and the value that was gained after experimental evidence was 6.626 into 10 is the power of minus 34 joules second. Okay, so this is an important value to remember. So this was the value that he gave, and this right here, the frequency, or in either of the case it's representing the frequency of the electromagnetic radiation that was absorbed or emitted. Okay, so now what we're looking at is that energy is not is not is not continuous. All right, energy is not continuous. Energy is available only in discrete values, and the smallest value that this energy could take was E is equal to hf. Okay, and after that, this energy could only change in multiples of hf, where n is an integer. All right, it's an integer. It could be 1, 2, 3, 4, and so on, but energy was always a multiple of hf. So the smallest energy that anything could possess, you could say, or the smallest packet of energy was when n was 1, and that would give you E is equal to hf. So this was the smallest packet of energy, and this uh, this small this small packet of energy is called a quantum. Okay, and a system can only transfer in whole quanta, right? It cannot give you fractions. What I mean to say is that a system cannot possess energy which is equal to, let's say, half hf. Nope, it's not, never in fractions. It will always be in multiples of hf, so always integer values. It could be hf, 2hf, 3hf, 4hf, and so on and so forth. So this is all that there was to Max Planck's experimentation and mathematical proof, and how the ultraviolet catastrophe was basically dealt with. This was actually followed by then we have another list of scientists who will then bring really things and concepts such as the photoelectric effect, defined by the Albert Einstein. These kind of things then come into physics, and it forms the basis of many of the things that we know today. It explained a lot of things that we couldn't before. So till next class, this is it for now. Till next class, Khuda Hafiz, and don't forget to subscribe if you liked the video. Till then, Khuda Hafiz.